Hi, chemmasters. I hope you are preparing well with our courses. Here in this video, we are going to analyze organic problems of CSIR June 2016 Chemical Sciences. So here you are going to get detailed mechanistic conceptual analysis of each and every problem. Now, just remember 5 steps whenever you are going to solve organic problem. Okay, the first step in which we should look at the possible functional groups on reactants which may involve in the reaction. The second step, we need to look at the stereochemistry on reactant. Is there stereochemistry or not on reactant? So here, the stereochemistry on reactant has the chance to affect the stereochemistry of product in many cases. Okay, that means so many reactions are stereospecific. So we need to look at the stereochemistry on reactant. The third step, we should look at the reagent and catalytic combinations. Fourth step, we should look at the reaction conditions. That means photochemical or thermal conditions in which the reaction is taking place. Fifth step, the solvent in which reaction is taking place, because the solvents can also change the reaction mechanism, and well-known, we can say the best well-known example for nucleophilic substitution reactions. Solvents, the polar and apolar and protic and aprotic solvents can affect the mechanism and differentiate the product. Okay, so if you have command and if you follow all these 5 steps, whenever you are going to solve an organic problem, then you can solve more than 90% of organic problems without error. Okay, right. Now just come to the point of the given question. Here we have given with allylic alcohol. Okay, so as in first step, we need to look at possible functional here, hydroxy group and alkene. Okay, right. So second step, there is no stereochemistry. And third step, look at the reagent combinations. We have CH2I2 and zinc copper. And we know that whenever we look at CH2I2 zinc copper combination, it is a well-known and a popular named reaction, that is Simmon-Smith reaction. And just remember that Simmon-Smith reaction is very important for various competitive examinations on chemistry. So just focus on Simmon-Smith reaction and get complete conceptual analysis on it. Okay, and just look at the video lectures on this reaction in our courses. Right. So when we know the named reaction which is involving in the given problem, then it is easy to find the next step. So simply in Simmon-Smith reaction, alkene converts into cyclopropane ring. So here cyclopropane will be formed in the first step. So here we can see the mechanism, how it will take place. CH2I2. So simply zinc copper insets in between carbon and iodine. Okay, so here we can get, and which will produce carbene, CH2. Okay, so carbene is produced here, and which is going to attack on this double bond and produces cyclopropane ring. And just remember that Simmon-Smith reaction is stereospecific reaction. That means if cis-alkene involves in the reaction of Simmon-Smith, then it produces cis-cyclopropane product. If trans-alkene or trans-allylic alkene is the reactant in Simmon-Smith reaction, then produces trans-cyclopropane product. Okay, right. So by that we can eliminate first one, and here just look at the reactant again. Here we have cis-allylic alcohol. Okay, so that's why two hydrogens must be same side, and methyl, and here CH2OH must be same side. So if you look at the third step where the two hydrogens are given trans to each other, so we can eliminate third one. Answer must be in second and fourth, because here the first step is correct one for that Simmons-Smith reaction. Now just look at the second step. Here, a ruthenium trichloride in water with a combination of sodium periodic acid produces ruthenium tetroxide reagent. Okay, so before going to find the correct product, we are going to check the oxidation of alcohol, that is primary alcohol, with that, so here primary alcohol with that ruthenium tetroxide. Okay, so I'll just check this mechanism. The lone pair of electrons and oxygen of primary alcohol attack on ruthenium, and then we can get this step. Hydrogen here, OH plus, so just compensate here, then we can get ruthenium. So just draw the complete structures here, and just remember that you should draw each and every step in detail, then only you will not get confusion. Okay, so the negative charge on oxygen going to attack on hydrogen, and bond goes here, and simply bond cleaves here. What you have get, the primary alcohol is converted to carbonyl product with the loss of ruthenium trioxide. Okay, with the loss of ruthenium trioxide, or and here we can say RuO4 minus H, and by taking up another proton, it will produce ruthenium trioxide and water. Okay, so simply here the ruthenium tetroxide just acting like a catalyst, right? Now, and further in the reaction we have water. Okay, so here just water is acting as a simply nucleophile going to attack on carbonyl carbon, right? So here we can get the next step as OH, and here OH. This is the step we can get, right, by taking up the proton. In the next step, ruthenium tetroxide again attacked by one of the oxygen of hydroxy groups. Okay, so here oxygen gets negative charge. Now just draw the complete structure. So just I'm not giving, proton just cleaves from it, and here ruthenium double bond O minus. So here we have hydrogen, and here we have CH3, and here we have hydrogen. Sorry, here we have OH. The negative charge going to attack on proton, and bond cleaves here, and ruthenium oxygen bond cleaves here. Okay, so what you will get? So simply CH3, just say, okay, C double bond O, OH, and C ruthenium O4 minus H plus, and by taking up another proton producing ruthenium trioxide in water. What you have get finally in final? So simply primary alcohol is converting into carboxylic acid functional group in the oxidation with ruthenium tetroxide. Now just look at the products second and fourth. Here we have aldehyde. In fourth we have carboxylic acid functional group. So fourth option is the correct answer. Okay, right. And in the next case, so just look at the next problem. As we said, just look at the first step. Here we have iodine and amine functional groups on benzene, and we have given with alkyne. And so third step, that is reagent catalytic combinations, we have given with palladium catalyst. And just remember that whenever we have benzene connected with halogens like iodine, and if we have given with palladium catalyst, okay, whenever these combinations are there, then we can simply thought that it is a coupling type of reaction. Okay, so the well-known named reaction or coupling reaction, that is Heck reaction. Okay, now just try to check the generalized reaction or the generalized reaction steps of Heck reaction. In the first step, palladium. So here, palladium catalyst through the oxidative addition. So here we have alkyl halide. So oxidative addition takes place here R and X. In the next step, alkene or here alkyne coordination takes place with that palladium. Here, just to take alkene. Okay, suppose we have taken generalized alkene. Then coordination takes place. Simply the pi interaction with that alkene takes place. Okay, here indicating ligand. In the next step, migratory insertion takes place. It is very, very important why the complex or the palladium complex should get migratory insertion. So here the possible reason is is to minimize the steric repulsions which are just rising from that bulk ligand. So here we have bulk organic, that means benzene ring. Okay, so that's why here migratory insertion is possible. And after that migratory insertion, so simply you will get palladium, here halogen, here the two ligands, and then after migratory insertion of alkyl group onto this alkene, we can represent here R and R prime. Okay, so we are just differentiating two alkyl groups. In the next step, beta hydride elimination takes place. Now just look at, we can give alpha for this carbon and beta for this carbon which is having hydrogen. So beta hydride elimination is possible. Here the bond cleaves here and the hydride eliminates from it, and this hydride going to attack or coordinate with this palladium. In this beta hydride elimination, we are going to get the product that is alkene. Okay, transalkene is major one when we compare with cis is also possible and produce it, but it is in minor ratio. Okay, right. And after this beta hydride elimination, you have remaining palladium catalyst as like this. So here we have X and we have hydrogen. Right. In the next step, through the reductive elimination step, here HX cleave from it, then we can get the catalyst again, and which involves in further process in this cyclic process. Okay, so here oxidation addition, oxidative addition, alkene coordination, migratory insertion, beta elimination, and reductive elimination. So through all of these steps, producing a coupling product. Okay, right. Now just apply same thing on given reaction. Okay, so first step, oxidative addition. So here simply the benzene ring, that means palladium. So here iodine, right? Palladium inserts in between benzene ring and iodine. So here we have L2, two ligands are there. Okay, so in the next step, here we have alkyne interaction. So here alkyne interaction with this palladium. So just draw in a clear way, so don't get confusion. Palladium, and which is having interaction with alkyne, and which is having functional group CH2 OH, and here trimethyl silyl group. Okay, and which is having iodine here and benzene ring. Okay, so benzene ring is having simply NH2. So just take it, and here we have two ligands. Right, here is the migratory insertion step. Okay, so this migratory insertion step is very, very important. because the bulk organic or simply benzene substituted benzene ring has the possibility to migrate here, okay, and here. So where it should migrate? It is a valid question. Okay, right. And then so simply the migration of organic group should takes place on this carbon instead of this, and palladium migrates here. Why it should takes place? I thought that silicon is having empty d orbitals, whereas iodine is having lone pair of electrons. So whenever the coordination, that means alkane coordination with palladium takes place, the lone pair of electrons and iodine interacts with the empty orbital of silicon. That's why trimethyl silicon drag palladium towards this carbon. In that case, the benzene ring, which should be migrated on this carbon only. Okay, so this is the possible. This may be the possible reason, right? And by that case, so what should happen here? The next step, simply just write down CH2OH, and here the benzene ring, and just write NH2. Here palladium, right? And which is having iodine, okay, and then here two ligands, right? Then here we have a trimethyl silyl group. Now there is a possible, that means palladium catalyst should be cleaved from it through the reductive elimination step. Okay, so palladium should cleave here. Whenever palladium tries to cleave from it, the lone pair of electrons, that means simply driving force here is the lone pair of electrons and amine nitrogen attack here, right? And palladium cleaves from it, right? So here we know that silicon having positive charge, whereas carbon having negative charge. So always silicon with partial positive charge and carbon with the partial negative charge whenever the bond between silicon and carbon. So it is never cleave from it. Only palladium should cleave. Okay, so simply through the reductive elimination, whenever lone pair of electrons attack here, the bond electrons goes on palladium and iodine cleaves from it, and we can get the final, that means the initial palladium catalyst. So here you have a new ring here, that is hetero ring. You can see this is the ring you will get. So here, okay, and double bond, here we have CH2OH, and here we have trimethyl silyl group, and here we have benzene ring. This is the final product. Now just check the options, and the nitrogen will having one hydrogen. Okay, so this is the final product. If you see the fourth option, it is the correct one. So answer 4 is the correct one, and I hope the analysis is helpful for you, and thank you very much.